Today, I want to talk about some work that we've been doing on extending STDP with synaptic delays. So, I've already been hearing a bit about delays, so this might be a little redundant, but just to frame the general concept, we have some sort of input current that is going into the soma of the neuron, and then we have multiple parameters that we can train that are controlling what generates that, aside from the input itself. So typically, you have weights and biases to modulate the amplitude, which are both operating in the same general space, as in working on the amplitude of the input signal, whereas delays are modulating the phase of the signal instead by time shifting the inputs. So the way we're looking at this is that if you have some presynaptic spike that's generated at a given time, it will be observed by the postsynaptic spike or postsynaptic neuron after a period D. And in Hebbian learning for synaptic delays, the adage I'm sure we've all heard hundreds of times at this point, neurons that fire together wire together. And for pair-based STP, we have typically two types of neuron pairs, either anti-causal or causal, based on the relative postsynaptic and presynaptic timing. Here, we also specify this conditionality on an anti-causal pair because the delay can shift a presynaptic spike that was generated in such a way that it would have been causal into one which is instead anti-causal. And for causal pairs, we increase the strength of the connection. And for anti-causal pairs, we decrease it. For weights, this is simple enough, and we've been doing it for long enough. They're proportional to the connection strength, and it follows. Larger weights, higher amplitude for a given input. Delays, though, instead, we're building off of some work from Nadafian and Gantanabish to say that here we're treating delays as inversely proportional to connection strength. And especially tying into what was just talked about, there's a certain intuitiveness in this, such that the larger the delay is, the more remote something is, which we can think of as the degree of proportional to strength. And to this end, we try to reintroduce this STP-based rule in as general of a form as we could get it. So for the weight updates, we have the gating by a postsynaptic activation for the potentiative term, and then proportional to the convolved presynaptic spike train up until the time t minus d. And for the presynaptic gating, here again, we're offsetting it by the delay d. The delay update rule takes the same general form, except now the potentiative and depressive terms are flipped, just because in order to match the previously described Hebbian formula for this. And we wanted to compare it directly to delay-related STDP, which is the work from Nadafian previously referenced. So the big thing here is that we're gating updates by generated postsynaptic and observed presynaptic activations versus just having them ungated. So to make this a little clearer, for DSSTDP, given two spike traces, we have the trace term, the gating term, and then we have the learning rates, A, versus using the offset and then the direct exponential on that. And in spite of the similarities, when you actually look at an example, in the short run, we can see the updates are pretty much proportional, although slightly different, using randomly generated spike trains, and here using a cumulative exponential kernel for DSSTDP. Over the long run, these diverge quite a bit. But beyond just some toy testing like this, we wanted to see if this would make a difference in an actual model. And for that, we decided to base our testing on the Deal and Cook model, but incorporating synaptic delays. So here we have a group of excitatory neurons, which are modeling the actual output that's used, and inhibitory neurons that are enforcing competition via lateral inhibition. The weights here are hyperparameters for controlling that, and there's no delay in these connections between the excitatory and inhibitory neurons. Instead, we have delays and weights, both trainable, between the inputs and the excitatory neurons. And then the training for this itself, going along with using STDP, is unsupervised. And then a classification is performed on the output of the excitatory neurons. Typically, this classification for a Deal and Cook model is based on spike rate. But while working on this, we thought that since we're incorporating delays, perhaps using time to first spike would be beneficial in some manner. And to that end, we add this idea of spike responsiveness. So inversely proportional to time to first spike and scaled between 0 and 1, so we could use it as a nice drop-in replacement regardless of spike length or anything else. And then the classification itself gives input to the network, and each neuron is assigned a class based on what class the samples come from, whichever those were would maximize that score. So for our experiment, like with the original model, we worked on MNIST, but reserved 10,000 of the training samples as the validation set, plus on encoded spike trains based on rate. We modeled our excitatory neurons with leaky integrating fire with an adaptive threshold, and inhibitory neurons also LIF, but no adaptive component. In all of these experiments, we also worked with a relatively small maximum delay, only 10 milliseconds, and in the discrete simulation, each time step was 1 millisecond. So a pretty brief window, really. And first, we wanted to look at the just rate-based classification accuracy, where the method we're introducing did perform the best across the 5 tested model sizes, or the 5 model sizes on which all of these approaches were tested. But we also see that as you get to larger models, DR STDP also outperforms it. And this pattern persists when using responsiveness rather than rate as the basis for classification. Going into that a little bit more to see if delays would work better with responsiveness, we can see that. Across all model sizes, STDP preferred using rates, whereas for 4 out of 5 with our method and 3 out of 5 with the comparison for a delay method, responsiveness was better. And plotting them using the best measure, we can see that persist. We also wanted to look at the update dynamics for a drop-in replacement, something that would be similar. And here we use the variance of learned weights over time as a proxy for the degree of training progress. And I'll say for DSSDP and STDP, the weight updates have the exact same hyperparameters. The different structure means for DR, we tried to just tune it for best results, but they're much more similar for these two. And during this, we also realized we had an opportunity to answer a bit of a question, which is, how do delays affect model capacity? And I think this also touches on some other points as we're getting into incorporating delays in models more broadly. Uh, some work has been done on this before, using a surrogate gradient method. Previously, I don't remember the authors off the top of my head. I'm sorry. But it was found that using a model with randomly initialized weights and trainable delays had roughly the same capacity uh, as one with just trainable weights. And so here we were wondering if there was any interplay between weights and delays specifically for this. And what we found as we extended out the size of the models without delays we tested, since a model with delays will have twice as many parameters, was that at smaller sizes, the delays were less efficient. There was benefit to just adding weights. Whereas once we started scaling out to larger models, at least for our new method, we can see that it becomes more efficient to use this second type of parameter rather than just falling back on increasing the size of what we already had. And there are a couple of developments that we hope to work with this in the future, which is first with a generalized approach using traces. We were interested in using triplets of spikes rather than pairs as the basis for updates. We also wanted to try a reinforcement learning by using a reward modulation component. And also, we were wondering if this could extend to supervised delay learning rather than the current delay learning resume method that's used, which uses a completely different delay update rule. If just using DSSCDP and following the same chain would result in a viable supervised method. Okay, um, happy to take any questions.
Great. Thank you very much, Marissa. That was great. All right, so the first question from Michelangelo, have you considered a variant of the triplet STDP rule, which I guess is your answer is on this slide, in fact.
The answer is yes. This is because we have effectively what we have is the saying that the presynaptic gating for it should occur whenever it's observed by the postsynaptic neuron, and because we can shift when in time we're looking at the trace, this should extend naturally to using a triplet model.
Cool. You haven't actually tried it yet.
Not yet, no.
Cool. Okay, great. The next question is about test accuracy. So SPK says, I guess that spike says your test accuracy, it looks like it gets to about 92%, which is what you get from a linear classifier. Do you have any hypothesis on why this happens?
Given the previous scaling, I would imagine that we get up that it would increase still. It didn't seem to be leveling out. I haven't tried running I have not tried running just the classifier on the raw MNIST dataset. However, from some other work which has been done with that, or at least a few people I've spoken to about that, I believe the accuracy of using the Diehl-Cook method for classification on the raw data would sit at about 68%. And the mid 80s to low 90s with larger models is in line with the work from the original paper.
Cool. Okay. All right. I think we have a bit of time for a few more questions. So let's go from one from Laurent Pernier. What's your intuition about the relative importance of the precision of weight and delay whenever they're quantized?
I think that the precision for delays can be much lower. The reason for that is this gets into a little bit of the implementation details, but for this in particular, since we're using an exponential model, we have that, and we know that there will be no additional spike in a window. We can just perform multiplication to get the exact continuous value delay between them. But even so, with a relatively large time constant, that delay offset isn't going to affect the magnitude of the signal too much in terms of how the synaptic kinetic model is changing over that window. So I think that just because you have you end up just having an integer delay if you use whatever the prior one was. You can just perform it that way. And in which case, the bottleneck there is that you have to, for any delay model, you have to keep the prior capital D time steps of data. So I think that precision for delays matters less.
Okay. Actually, I have this, it relates to my question that I had,
Hmm.
which is, do you think the results would be different if you looked at a more temporal data set, which might make more sense given you've got delays? Because MNIST is just static, right?
Yes, that is actually, I think that as you work to a more temporal data set, delays will make a bigger difference. Picking one that didn't have that was a decision for us in testing because one thing that we were wondering is even if there was no inherent temporality to the data set beyond just whatever the generated spike trains were, if it could still make some use out of that capacity versus not using it in any way.
Okay. Yep, that makes sense. Okay, I think we'll just ask one last one from Tim Masquelier,
Hmm.
which is, could you learn the optimal delays using backprop and then see how far your STDP rule gets from whatever backprop is finding? And maybe you can use that to inform tweaking your STDP rule or something like that.
That's interesting. Let's see. There are at least to the best of my knowledge, there are surrogate gradient methods that do work with delays. So yes, I believe you could do that. You could, if you fix the weights or learn the weights of STDP and use a separate backprop method for the delays, that should give you an idea of how similar they are, with the one caveat that there may be multiple potential sets of delays that are equally good or similarly, and you're not guaranteed to find the exact same one with a backprop based approach. But I imagine you could use some heuristics there to see roughly if it's landing in the same place.